We're doing the elastic and inelastic collisions number 3. So we have a cart colliding with a bumper. So here we're not going to have momentum conserved because the bumper is an external force on the system. But if we use some of the techniques that we used in the first problem, we can actually still deal with this. Or actually, even in that football player problem from the first recitation packet. So determining the final velocity of the cart after the collision. Okay, so what we did before was we noticed that the F net on the cart is just that normal force from the bumper, which is given up there, which is the mass of the cart times the acceleration of the cart, which would be delta V, over delta T. So we're trying to find the delta V. In order to do that, since this is the average acceleration, we need the average force. Okay, so how do we find the average force here? Well, there are a lot of different ways to do it, but since this thing is nice and linear, the average of each section is sort of at the midpoint. So you can imagine chopping off this. So chop it in half first. Chopping off this top little triangle and folding it under here, and it would fit exactly, just like we did with average velocity in kinematics in CAPM. Right, the average velocity is the velocity at the midpoint when the change is linear. So the average force here is 4.5 newtons. Okay, so we're solving for delta V. So it's average n times delta T divided by the mass. And delta V is Vf minus Vi. So I'm going to bring the Vi to the other side. So Vi plus n delta T over m. So this term right here is actually giving us the change in velocity. So it's 3 meters per second. And here's where we have to be careful with our signs, because if our Vi is positive 3 meters per second, when I look at the force diagram, that n is to the left. So the n I'm going to have to use here is negative, or I could have a positive force and a negative velocity, but I have to make sure the signs agree. Always make sure those agree. So diagramming is really important to do that. So that's negative 4.5 newtons times 2 seconds is how long the whole thing lasted, divided by 0.2 kilograms. This is what we get from that. Oh, well, yeah, negative 1.5. Didn't need a calculator on that one, actually. So this is to the left. Was it elastic? Well, for it to be elastic, we should have the same amount of Ke at the end that we did at the beginning. And our initial Ke was just from the cart, and our final Ke also just from the cart. And because the V's are not equal, it was not an elastic collision. We definitely lost some energy here. We started at 3 meters per second and ended at 1.5. So K final is less than K initial. This was an inelastic collision. If you have a perfectly elastic collision, if you want to look at it in terms of collision, this was colliding with the Earth, and the Earth, I guess in principle, moved a little bit, but not so much as we'd notice. So if you're looking at a tiny object versus a giant object, we're assuming that the giant object is staying at rest. An elastic collision would mean that the tiny object would bounce off with the same speed that it went in. So this cart would come back at the same speed. Even if you account for the motion of the Earth, it would be vanishingly small, which means that the final velocity of the cart, if this were elastic, would be really, really, really close to -3. So in the like 15th decimal place or something, it would be different. If you drop a ball on the floor, it should come up with the same speed that it went down if it's perfectly elastic, so it would come back up to the same height you dropped it from. They never really do that, so our bouncy balls aren't really elastic, but they can be close.